p-series test. So the p-series test for convergence is probably one of the nicer tests that basically simplifies down the integral test. But really, we can only use it when we see a series in the form of 1 over n to the power, so to some number powered exponent. So for instance, when you're looking at our series, it's going to be 1 over or 2 over or 3 over some value to some numbered exponent. Now, we have two outcomes that are possible. This condition of convergence is if p, that powered exponent, is greater than 1, right? So we all know that that function converges, but it diverges if it's less than or equal to 1. So just to kind of give you a sense of what this would look like in an expanded form, that powered exponent, whether it's 1, 2, 3, whatever it is, you would typically see a series go 1 over 1 to the second plus 1 over 2 to the second plus 1 over 3 to the second, or again, whatever that powered exponent is. So the way these problems work is we want to identify a number over n to an exponent. It needs to be a single n in the denominator, and it has to have that positive exponent. So in the case of our first example here, we can identify that powered exponent. So if we look at our n that's in the denominator, we see that the powered exponent is 3. So that means our p-value is 3. And according to the p-series test, since p is greater than 1, this series is going to converge. So similarly, over here on the right, we have a series that is 1 over radical n, but since we know radicals can be rewritten as powered exponents, we're going to rewrite this as n to the 1/2 power. And since our exponent is 1/2, that means p, our power, is 1/2. And since p is less than or equal to 1, that means our series is going to diverge. Now, remember, it doesn't matter if it's like a 3 over n, a 4 over n, it just has to be some number, some constant over n. So take a look at some of the practice. Sometimes you might have to do some rearranging, but ultimately that's the p-series test.